let's get started. So welcome everyone to today's algebraic geometry seminar. So today we are happy to have Professor Sho Tanimoto from Nagoya University, and he will speak about sections of Fano vibrations over curves. Yeah, please.
All right. Thank you for the introduction, and then thank you for the opportunity to give a talk. I'm very excited. So title is sections of Fano vibration of a curve. So I am an arithmetic geometer trained in arithmetic geometry originally at the Kura Institute, and then so since I was a student, I have been studying Marin's conjecture, which is a conjecture simple formula for the counting function rational points on Fano variety. And then when you count rational points, it is important to exclude some contribution from exceptional set so that a simple formula reflects like a global geometry of underlying variety. And with Brian Lehman, I've been studying like geometry, birational geometry of this exceptional set using higher dimensional algebraic geometry, such as the minimal model program and so on, and BAB conjectures and so on. So I think I'm gonna first talk about this study of exceptional set using higher dimensional algebraic geometry. Then another half I'll talk about application of this study of exceptional set to understand geometry of sections on Fano vibration, especially like a moduli space of sections on Fano vibrations and so on. So this is the theme of this talk. All right. So I'm gonna start. Sorry. So first, I'd like to talk about exceptional sets in Marin's conjecture. So this is joint work with Brian Lehman and Akash Kumar Sengupta. He's a postdoc at the Columbia University. Okay. So now, I was told that I should make first 30 minutes somehow understandable for like a grad student. So I'll start gently and then give a bunch of introduction. So Marin's conjecture is about like a simple formula for the counting function rational points. So on Fano variety. And so, I mean, in our situation, there are infinitely many rational points. And then you like to count rational points. To do that, you need to introduce some kind of size of rational points so that rational points of bounded size is finite so that you can count and consider like a single formula as size goes to infinity. And this size is given by height function, which measure arithmetic and geometric complexities of rational points. So here's an example of height functions. So let Pn be the n-dimensional project space defined over rational numbers. And then height function is the real valued function on the set of rational points. So, I mean, this is like a usual notation for scheme, but if we have like a kind of scheme variety, and then we wrote like this, then this means that this is set of rational points over Q. This is a set of rational points over Q, and this is defined by this. So now, of course, I mean, if you have points on projective space, then you can choose homogeneous coordinates so that the xi is integer because the point is only defined up to scalar. So you can assume that points as homogeneous coordinate integers and GCD is equal to 1. And then for such like a homogeneous coordinate, we assign max null. This is the example of height function on projective space. And note that now set of rational points P whose height is bounded by T. This is a finite set for any real value T. And this is so-called like a Northcott property. So the set of rational points of bounded height is a finite set. Okay. Now, so I'm not gonna give you general definition of the height function, but I'm gonna give you some information. So suppose we are given a number field F, and then projective variety X defined by F, and the Cartesian divisor L on X. then one can associate height function to triple FXL, and height function HL is real valued function on the set of rational points. And then moreover, when L is ample, then no scope property again holds. So that means that for any subset of a set of rational points, you can define this counting function as set of points in Q such that height is bounded by T. So this is a finite value. So this is well defined. And then we are interested in like a single formula for this counting function as T goes to infinity for appropriate choice of Q. I mean, we need to choose this Q in wise way so that this I think formula of this counting function reflects the global geometry of X. So that's the kind of idea of Marlin's conjecture. All right. Okay. So I'm gonna so far do you have any question? Are you okay?
Yeah, I think we are okay.
Yeah, all right. So then so this is a finite function. And then so I like to introduce Marlin's conjecture. So I like to formulate Marlin's conjecture. And to do this, I need to introduce a bunch of invariants, bilateral invariants in Marlin's conjecture. And then so as a formula is expressed in terms of these bilateral invariants. So I'm gonna define it. So suppose sorry. So but before doing that, I like to introduce some terminology of a higher dimensional algebraic geometry. Some of you might know these terminologies, but anyway, let me define those because I was told that I should speak for grad student for first 30 minutes. So I like to define them. So now let F be a field of characteristics 0. X is a smooth projective variety defined by F. And L is a Q divisor. So DI is a prime divisor. So like a codimension 1 reducible variety, subvariety of X. And AI is rational number. AI is rational number. And then we consider like a finite sum, linear combination of these prime divisor over Q. This is so-called like a Q divisor. And then take a curve, C, proper one-dimensional curve in X, then one can define intersection number L dot C. So when L is like a prime divisor and C is an honest curve meeting L transversely, and this number is the exact number of intersection points. So in general, when it doesn't meet transversally, but it doesn't contain the prime divisor, then you need to count points with multiplicities. And when C is contained in prime divisor, then we need to do something. Like we need to either use a moving lemma to say that, okay, this divisor is linear equivalent to some other divisor which doesn't contain C and so on and so on. And anyway, so one can define this intersection number in many ways, but there's some well-defined number and it's bilinear pairing and so on and so on. And then we say L is an F if for any curve C in X, L dot C is non-negative. So this is the definition of Neffness, divisor is Neff. And then we say L is big if L is expressed as a sum of ample Q divisor and the effective Q divisor. Effective means that all AI is non-negative. That's the effective divisor. Well, then ample means that, so basically like some multiple defines embedding into projective space and so on. And then big means that it's expressed as a sum of ample divisor plus effective divisor. And it is important, these are the Q divisor. Even L is integral, those A and E doesn't need to be integral. So anyway, okay, so that's the definition of bigness. Okay, now I'm gonna introduce numerical equivalence. So two divisors, two Q divisors, D1 and D2 are numerically equivalent if D1.C equal to D2.C for any curve C in X. And in this case, we write like a D1 is numerically equivalent to D2, and we use this symbol. And then look at like a space of Q divisors. This is a vector space, infinite dimensional vector space. And then quotient by numerical equivalence. And then this is so this is important theorem in algebraic geometry that this is a finite dimensional vector space over Q and called as a Néron-Savary space. And then also like N1X is tensor of N1Q over R with R. So N1X is real finite dimensional real vector space. Okay, so this is a Néron-Savary space. Now, two real one cycles, alpha beta. So one cycle means that this is a formal sum of linear combination, formal sum of curves, proper irreducible curves. And then real means that coefficients are real numbers. And two real one cycles, alpha beta, numerical equivalent, if for any Q divisor D, D dot alpha is equal to D dot beta. And again, we write like this numerical equivalence by this symbol. And again, look at the space of real one cycles. This is an infinite dimensional vector space. And then we take a quotient by numerical equivalence. So this is and then by definition, Néron-Savary space is dual to N sub 1x. So in particular, this N sub 1x is also finite dimensional vector space. Okay, so those are two vector spaces I frequently use in my talks. Okay, and then so now this is Néron-Savary, real Néron-Savary space, and inside this we have a comb of NEF-R divisors. And then also like a real one cycle alpha is NEF for any effective Q divisor D on X, D dot alpha is non-negative. So also we define notion of NEFness for real one cycle. And then we consider like a NEF comb of curves. So NEF comb of NEF cycle, comb of NEF cycles. And then these are strict closed convex cones and so on and so on. So this is really closed convex cone. Also inside Néron-Savary space, we consider effective cone of effective R divisors. So in general, this doesn't need to be closed. So we take closure of this. This is another strict convex closed cone. And this is called as a pseudo-effective cone of divisors. And then in same way, we look at the cone of effective real one cycles. And this doesn't need to be closed in general. So we take a closure of this. And this is called as pseudo-effective cone of curves. And then by definition, NEF cone of curves is dual to pseudo-effective cone of divisors. And then NEF cone of divisors is dual to pseudo-effective cone of curves. And then we have such a dualities. So these notations I frequently use in my talk. So I just introduced especially for grad student. Anyway, so that's main ingredient I need from a high dimensional geometry to define them. All right, then I'm gonna define birational invariance in Manin's conjecture. So now here's the definition. Let F be a field of characteristic 0. X is a smooth projective variety defined by F, and L is a big Q divisor, and Kx is the canonical divisor of X. So canonical divisor is like a characteristic divisor whose associated line boundaries is isomorphic to top exterior power of cotangent bundle. So that's a canonical divisor. All right. Then Fujita invariant or A invariant is this. So AXL is defined as minimum real number T such that TL plus KX is pseudo-effective. So this is some, in general, irrational number. It doesn't need to be rational in general when you only assume that it's big. So when you assume that this is big and F, then this is a rational number by BCHM, Bidukar, Castellini, Haycon, McCann. You can prove that this is a rational number when L is big and F. And then basically we only consider a case where L is big and F. But in general, this is a irrational number. And then when L is not big, we define A to be formally set to be infinity. So this is just like a notation. Okay, so then by Boxom, Demari, Pampitane, I think this is published in JAG. When L is big, then So by definition, A is positive if and only if, this is just by definition, Kx is not pseudo-effective. And Kx is not pseudo-effective is equivalent to say that X is geometrically uniroot. That means that it is covered by rational curves. So there's some moving family of curve which dominates X. Moving family of rational curve which dominate X. That's what geometrically uniroot means. Okay, so this is by Boxon, Demari, Palm, Pitane. Okay, so this is, so in particular, in my talk, I'm only interested in variety whose invariant is positive. So that means that we are only interested in varieties of uniroot type. Okay. Now, assume that A is positive, but first assume that A is finite. So it is big, and then A is positive. And then we define face of Nefcon curves to be this. So now L plus Kx is pseudo-effective. So in particular, this has a non-negative intersection against any Nef1 cycle. So in particular, this intersection will cut out some face, extremal face of this strict closed convex cone. And this is the external face of Nef cone, and we define B invariant to be the dimension of subspace spanned by this face. Okay, so this is the definition of B invariant. And then so far we define these AB invariant for smooth projective variety. But also I like to define those invariants for when X is singular. So when X is singular, we take smooth resolution and define A invariant and B invariant to be the pullback of A invariant and B invariant of pullback. And then these are very defined due to bilateral invariance of AB invariants. So if you have some, so when X tilde and X are smooth, then those invariants are bilateral invariants. Okay.
So when you assume that A is strictly positive, so in particular, the canonical divisor is not big. Or...
Right. I mean, assuming smooth, yes, yeah.
Thank you.
Yeah. So as we are assuming canonical divisor is not pseudo-effective, yeah. But yeah, right. All right. Now let me give you an example of this invariant. When X is smooth Fano variety defined by F, that means Fano means that minus Kx is ample. And let's say it to be the anti-canonical class, then A invariant is equal to 1 because, you know, this is, I mean, when T is equal to 1, minus Kx plus Kx is 0. So it's hitting the boundary. So invariant is 1 and B invariant. Now L plus Kx is just a 0 divisor. So this face is the entire cone. So space spanned by entire cone is equal to n sub 1x. So dimension of that is equal to space of dimension of Néron subgroup space. So that means Picard's number. Okay. Right. Now, so next, I'd like to introduce the Manin's conjecture. So to do this, I need to introduce a notion of syncset. So this notion first embedded by Hilbert and Serre in the study in the context of a Galois inverse problem, inverse Galois problem, or Galois inverse problem, whatever. And then, so anyway, let me give you a definition. So let F be a number field. X is a variety defined by F. And a type 1 syncset is VF. So set rational points on B, where B is the proper closed subset of X. B is the proper closed subset of X. Type 2 syncset is image of rational points on Y, where morphism F from Y to X is a dominant generically finite morphism of degree greater than or equal to 2 with Y's integral. So this is so-called, and then we are looking at image of rational points on Y. This is type 2 syncset. So let me give an example of type 2 syncset. So on affine line, set of square is a type 2 syncset because this is the image of a square map. Right? So we have map from A1 to A1 mapping X to X square, And the image of rational points on A1 is exactly a set of squares. So this is so-called type 2 scene set. And then scene set is any subset of a finite union of type 1 and 2 scene sets. Okay? So, right. So this is the notion of scene set. And the important thing is this theorem. So set of rational points on project space is nothing. So for example, like when X is smooth and so when set of rational points on project space is so in particular, so when X is rational over ground field, then set of rational point is nothing. You can prove that. And then moreover, assume that X is smooth projective geometrically rationally connected variety over F. So rationally connected means that two general points can be connected by rational curve. So that's rational connected means an example of such a rational connected variety is a smooth Fano varieties. And then if Coriolis conjecture is true, that means that Brownian obstructions are only obstruction to weak approximation. Then set of rational point is nothing as soon as there's a rational point. So Coriolis conjecture predicts that set of rational points is dense in so-called Brahmani set. And if this conjecture is true, then set of rational points is nothing as soon as there's a rational point. This is a bit surprising because once you find a rational point, you are guaranteed that there are infinite many rational points and there are infinite densely dense set of rational points and so on and so on. So it's a bit surprising conjecture, but it's not that surprising in the sense that, for example, for conic or quadratic hypothesis, as soon as you find rational points and it's rational and it becomes like there are tons of rational points. So far there's no counterexample to this is predictions. So anyway, so we are expecting that for Fano varieties, set of rational points is not thing as soon as there's rational points. All right, so here's a conjecture. Here's a conjecture. So now, so this is Manin's conjecture. This formulation is like contributed by Bartleff, Victor Bartleff, Yuri Manin, Emmanuel Pear, and Yuri Chinkev. There are a bunch of people who contribute to this contribution. So sometimes this conjecture is called like a Bartleff-Manin pair conjecture or Bartleff-Manin's conjecture. But anyway, I mean, I like to call it Manin's conjecture because there are many people contribute to the formulation. So anyway, so now let F be a number field and X is smooth projective geometrically rationally connected variety over F. And L is Bicknell Q divisor on X with Erdrich metrization. So you can ignore this terminology. This is needed to define height function, but you can ignore this. And then suppose that set of rational point is nothing. Then there exists some scene set such that after removing set of rational points on Z, counting function behaves like a constant C times t to the A times log t to the B minus 1 as t goes to infinity. Where these A and B, those are variation invariants I just introduced before. And this C is pairs constant introduced by Emmanuel Pear for anti-canonical divisor and the Bartleff-Schinkel for arbitrary weak divisors. And this set Z is called as the external set, which is the main theme of this talk, first part of this talk. Now, so originally around 90s, it was expected that this set Z is not that dense. So it should be contained some proper cross subset. So you can take a C so that set of Z is set of rational points on proper cross subset. So type 1 scene set. However, there's a counterexample found by Bartleff-Schinkel first. So in general, it is possible that external set is dense. And then first person who kind of suggested to use scene set in Manin's conjecture is Emmanuel Pear around the beginning of this century. And then this conjecture has not been paid attention for a long time, but recently there are a bunch of examples where we can prove Manin's conjecture after removing Zariski dense thin exceptional set. So this conjecture, now people start to believe that this conjecture is correct. Anyway, all right. So let me explain why do we need Z to be thin set. So this is a dead example by Bartev-Chinke. So now let F be let F be a number field containing square root of -3. Let X be a Fano 5-fold in P3 times P3 defined by this equation. This is like a in bihomogeneous polynomial. And then so this is a Fano 5-fold, and the we let L to be the Anchor class. Then by Lefschetz hyperplane theorem, Picard rank of X is 2. So if cross-set version of Manin's conjecture is true, that means that we can take this exceptional set to be proper cross subset, then there exists some Zariski open set such that that counting function of this Zariski open set behaves like a C times log T because the B invariant is 2. However, consider the projection to P3, and then for fiber, take a point on P3, and the fiber is a cubic surface, because if I fix xi, then this is the cubic equation, and this gives you a cubic surface. And then moreover, when these xi's are all cubes, then Picard rank of xp is 7. As you know, Picard rank of a cubic surface is 7 over algebraically closed field. But doesn't need to be over the non-closed field. But when xi's are all cubes, then you can say that all lines on cubic surface is defined over the ground field. So in particular, Picard rank is 7. Thus, Manin's conjecture for this singular smooth cubic surface claims that this counting function of fiber behaves like a C times T times log T to the 6. And this is the contradiction. There are more rational points on the fiber than total space, and it's not compatible. And then Bartev-Chinke showed that X cannot satisfy cross-set version of Manin's conjecture. So this is the first example, counterexample to the closed-set version of Manin's conjecture. All right, there's another example by Le Dirichlet. So now let S be a P1 times P1 defined over Q. Now let X to be the Hilbert scheme of 2 points on S. So this is a weak Fano 4-4. So Hilbert scheme 2 points on S. Basically, this is the parameterizing length to zero-dimensional subscheme on S. So like a 2 points, basically 2 points. And then when 2 points collide, then we also need parameter tangent vector. That's a Hilbert scheme 2 points. And then let's L to be the minus kx. And then A invariant is 1, as I told you. For Anchor class, A invariant is 1. And B invariant is equal to Picard number. And Picard number in this case is 3. So it's 3. On the other hand, we have this diagram. So X mapping to symmetric product of S. This is now S times S, and then we have involution, swapping coordinates, and take the quotient. This is a symmetric product. And then there's a Chow-Hilbert morphism from X to symmetric product. And then to get the morphism from this guy to this guy, we need to blow up a diagonal. And this is a W. And then we have such a commutative diagram. And then one can so this phi is Crepant resolution. And the anti-kernel divisor on this guy proves to anti-kernel divisor of X. So using this, one can prove that invariant of W of F star L is equal to invariant of S times S, which is this, and then 1, and B invariant of W is equal to this B invariant, which is equal to 4, because Picard rank of S is 4. Thus, because S is just P1 times P1 times P1 times P1, so Picard rank is 4, thus X cannot satisfy cross-set version of Manin's conjecture. And the Le Dirichlet shows that after removing contribution from W and some proper cross subset, X satisfies Manin's conjecture. Okay. So those are examples I wanted to mention. Right. Do you have any question?
So for Batiev, Jinko's counterexamples, of which thing set should we remove to get the correct statement?
So basically, like we need to remove like split fibers of Picard line greater than equal to 2 and a contribution from lines and so on, so on. But actually, those things actually there's a way to define this exceptional set, and then computing this exceptional set. For this example, my PhD student is working on that, so his paper will appear soon on arXiv. But anyway, I mean, even computing exceptional set is highly non-trivial in general. But I mean, my student computed exceptional set for this example. I think he's in this talk. I mean, on the Zoom. Gao, yeah. But anyway, I mean, his preprint will be available soon. But even computing external set is pretty tricky. And then actually, unfortunately, even like proving a cubic surface, so there's no single example of a smooth cubic surface where we can prove Magnus conjecture. Unfortunately, it's really hard for smooth cubic surface. So proving Magnus conjecture for this Bartlett-Chinkill example is much, much harder. And then, so right now, this one is not proved. There's no proof right now. But for Ludwig's example, we have a proof. She amazingly proved this example by counting the quadratic points on P1 times P1.
Okay, thank you.
Yeah, thank you. All right. So then I'd like to get to our main theorem. So this is joint work with Brian Lehman and the Akash Kumar Senguta. So let F be a number field F. X is a smooth geometrically uniruled projective variety over F. L is big and negative divisor on X. Now let Y F run over all generically finite morphism from Y, from smooth projective variety Y to the image such that this inequality holds in the lexicographic order. That means that A invariant of X is less than equal to A invariant of Y, and if it's equal, then B invariant of X is strictly less than B invariant of Y. So this is this inequality hold in the lexicographic order, and consider such automorphism, and then take a union of image of rational points of this morphism. And then we prove that this is indeed syncset. Okay, so what's the idea of this theorem? So if X and Y satisfy this inequality, and moreover, asymptotic formula of Magnus conjecture holds for X and Y, then asymptotic formula of Y is strictly bigger than asymptotic formula of X. So it is natural to include contribution from such a Y to exceptional set. Then natural question is, if I take union of those contributions with Y, is this syncset? And then we actually prove that this is a syncset. And then I'm not going to give details of the proof, but the proof uses a higher dimensional algebraic geometry. So basically, we use the minimal model program and BCHM a lot. And also, we proved recent theorem Bilka proving BAB conjecture. That means that boundedness of singular Fano varieties. So we need this conjecture. And also we need some input from arithmetic geometry. Hilbert's reducibility theorem, and then systematic usage of entire fundamental groups and the homotopy lifting property with rational base point. So basically, maybe we call it like a Y satisfying this inequality is like accumulating morphism or accumulating maps. And then we constructed bounded family of accumulating maps using BAB. So, but then problem is these are accumulating maps over algebraic class field. You can construct such a bounded family using BAB. But this doesn't need to be bounded over algebraically closed, non-closed field because of twist. So we constructed some universal family of accumulating maps which satisfy universal property up to twisting. So after allowing twisting, it satisfies universal property. And then Hilbert's divisibility theorem is used to prove that contribution of those twists are thin set, is contained in thin set. So this is the idea of a proof. Anyway, okay. So that's the first part of the talk. I just spent 30 minutes. I think I'm on the track. So do you have any question?
Yeah, I think so far so good.
Yeah, okay. All right. So anyway, that's the main theorem. And then this essentially uses BAB conjecture. All right. Now let's change the gear and then moving to like geometry, algebraic geometry. So I'm going to apply this study of external set to study a moduli space of rational curves and moduli space of sections. So second part is about non-free sections of Fano fibrations. And this is joint work with Brian Lehman and Eric Riedel. All right. So now Manin's conjecture over function field. So far we've been thinking about Manin's conjecture over number field. But we can also consider Manin's conjecture over function fields. And then, so now from now on, I'm going to walk over C. And let B be a complex, smooth projective curve. Okay. And the Fano fibration is a morphism from X to B such that X is smooth projective complex variety. B is smooth projective complex curve. Phi is flat with connecting fibers. And the genic fiber of pi is a Fano variety over the function field. Okay. So we are interested in Fano varieties over the function fields of curves. And then it's natural to consider such a model of this Fano variety over the function field. And then this is given by Fano fibration. And then we are interested in rational points of Fano varieties over function fields of curves. And then by variative criterion of properties, it's equivalent to think of sections of Fano fibrations. And then to do this, so from now we consider like a space of sections of pi, and denote this by SEC X over B. So this is a space of sections. This is an open subset of Hilbert's scheme of X, and this consists of countably many irreducible components. And then, so then I like to mention that when Fano fibration is a trivial family, that means that it's product. Then space of section can be identified with a space of morphism, parameterizing morphism from B to X. So our study also has an implication to space of morphism, but I'm not gonna touch on this. I mainly focus on space of section from now on. But our study also has something to say about morphism scheme. Okay. Now, let me recall some deformation theory of space of sections. So let M be a so when I say component, I mean irreducible component. So let M be a irreducible component of a space of sections. Then dimension of M is always greater than or equal to this number, where minus kx is the relative anti-canonical class, and then C is a member of M, and then G is a genus of B. So this is so-called, right down, this number is called like an expected dimension. And then expected dimension is always lower bound for dimension of a moduli space. We also have inequality that dimension of M is bounded by expected dimension plus H1 of cohomology. H1 of this relative tangent bundle. Restricted relative tangent bundle. And then when this cohomology vanishes, then we have equality because lower bound and upper bound is the same. So this cohomology behaves like a obstruction space of deformation. Okay. All right. Now, so I'd like to introduce geometric Manin's conjecture. So in his handwritten notes in 1988, Bartleff developed heuristic for Manin's conjecture over global function fields. this rely on the following predictions about the geometry of a moduli space of sections. So basically, like Butler came up with like a Manning's conjecture for over function field of curves over finite fields. And then his conjecture is the heuristic is rely on some properties of moduli space or sections. And then so original property he predicted are not correct in general, but then we came up with some correction. I came up with this correction of this heuristic with Brian Lehman, and then this assumption of this heuristic are now called like a geometric Manning's conjecture. And then I'm not gonna give full details of geometric Manning's conjecture, but I'm gonna give you some like a rough ideas of this conjecture. So this conjecture is the following conjecture. So first one is the fictional set. Pathological families of sections are controlled by Fujita invariant. So pathological families, I mean, so I'm gonna explain later. But anyway, so our main theorem can basically settle this prediction over complex numbers in full generality. So that's our main theorem. And the uniqueness, so there's a unique non-pathological component of space of section, which should be counted in Manning's conjecture for sufficient positive algebraic class alpha of sections. And we call this unique component as the Manning component. So now, so basically you can think of this as for any NF class. This is not correct in general, but you can think of this as for any NF class, algebraic class of section, this space of section is reducible or something like that. That's what we like to say. And then stability, Manning components of section exhibit homological or motivic stability as degree increases. Okay. And the idea of using homological stability in Bartlett heuristic is due to Ehrenberg and Banketesh. So what we like to do, so what this means, so basically we like to count number of rational curves or number of sections defined over finite fields. And then this is amount to count number of FQ points or moduli spaces. So then it's not, so to count number of FQ points, it's natural to use Grothendieck-Lefschetz trace formula. And then Grothendieck-Lefschetz trace formula requires to understand homology of moduli spaces. So in this way, we need some kind of homological stability of moduli spaces, the components of moduli spaces. So this is the basic idea of geometric Manning's conjecture. And then basically we prove this first prediction in full generality over complex numbers. All right. So now what we mean by pathological components? So we mean this by no free class. So what do we mean by free? So now here's the definition. Let x pi x over b be a Fano fibration. Then section C of pi is relatively free if restricted tangent bundle to C is globally generated and H1 is equal to 0. So that's the definition of relatively free. And then this is nice because if it's, this property is satisfied, a section component parameter such a section has expected dimension because H1 is vanishing. And then also because it's globally generated, it means that evaluation map is dominant. So it covers an entire space. So this is a very nice property to have. So on the other hand, if component contains free section, relatively free section, then general member is relatively free. So it's nice. So problematic component is a component which only contains non-relatively free sections. And then this is hard to analyze because we don't know what the dimension is. Differential theory doesn't work in a nice way, and so on and so on. So it's really problematic. And then, so here's our main theorem. This is joint work with Brian Lehman and Riedel. And then we just posted this preprint in this January. So it's already available on archive. Anyway, so now let pi x over b is a Fano fibration. Then there exists some Xi number, real number Xi, and T with the following properties. So M is a reducible component of a space of section parameterizing a family of non-relatively free section, which satisfy that anti-canonical degree is greater than or equal to C. So this is a component parameterizing non-relatively free sections of sufficiently large anti-canonical degree. Now, let U nu be a normalization of universal family over M, and let EV denotes the evaluation map. When evaluation map is not dominant, then subvariety Y swept out by sections parameters M satisfy that M variant Y, genic fiber Y is greater than or equal to M variant of genic fiber of X. Actually, by the way, this is just equal to 1, but anyway, M variant is greater than or equal to M variant of X. So, this is nice because subvariety like this, we know how to compute. BAB and so on, and our study of external set give it you like a way to understand these accumulating subset, accumulating subvariety. Subvariety satisfying this inequality. We have access to that. So this is nice. Now, when evaluation map is dominant, then let F from Y to X be the finite part of Stein factorization of evaluation map. Then we have M variant of Y is equal to M variant of X. Furthermore, there's some rational map from Y to Z with the following. So this is B rational map. This is B rational map with the following property. Let's see the general section on Y. Since this is Stein factorization evaluation map, section parameterized by M naturally sitting on Y. And then let W be the resolution main component of closure of fiber of C, image of C. Okay. Then we have that M variant of W is equal to M variant of X. And the eta dimension of this adjoint divisor is 0. And then street transformation of the general deformation of C in W is relatively free in W. And then sublocus of M parameterizing deformation of C in W has codimension at most T in M. So last condition saying that basically like C moves a lot in W, like moves a lot in the fiber, but not just to cover like a Z. It does cover Z, it does move to cover Z, but not much. And it moves a lot in the fiber. That's fourth condition is saying. So this is nice because now this W is again some kind of accumulating map. We don't have to compute. We can characterize, we can compute, we can classify using a BAB and so on. So this is very nice. And then we can say that, so these sections, these non-relativity sections are actually coming from accumulating maps. And inside accumulating maps, those sections are even free. So it's a very nice theorem, somehow way to compute those sections. Okay. All right, let me give an example of this type. So let X over B be a Fano fibration over B such that generic fiber is smooth cubic hypersurface of dimension greater than or equal to 5. Okay, so this is the base generic fiber is cubic hypersurface. Adjunction theory tells you that there's no generic finite morphism from Y eta to X eta such that M variant of Y is greater than or equal to M variant of X. There's no such accumulating map. So our main theorem 1 implies that general section of sufficiently large anticanonical height are relatively free. So you can prove that all components of sufficiently large anticanonical degree parameterizes free section. So, it's very nice application. You can say something concrete about actual examples using our main theorem. Another example. So let me give an example of these accumulating maps. Let X be a smooth cubic threefold, B is a smooth project curve of genus G, and MD is a component of morphism scheme parameterizing degree D multiple covers from B2 line on X. Then expect dimension is 2D plus 3 times 1 minus g. However, actual dimension MD is 3D plus 3 minus g. So in particular, when genus is greater than or equal to 1, then actual dimension is strictly bigger than explicit dimension. So in particular, these components never be free. And then let's take like a universal family of lines. And this is like a, then let y to be, then y is like basically u. And y to x like a evaluation map and generically finite and so on. And then w is a fibrillation of lines over B. Indeed, any line satisfies that L minus kx is equal to x minus kx. So in this case, accumulating maps, actually lines. Okay? So these are kind of concrete examples. You can use it to prove that so all non-free sections are coming from like lines. Okay. Right. So this is a first set main theorem. So I'm going to move to second main theorem. But so far, do you have any question about the main theorem 1? Okay, it seems like there's no question. All right. So then I'm gonna move to main theorem 2. So main theorem 2 is the following. Let pi x2 over b is a Fano fibrillation. Then there is some proper cross subset in X such that any component M of a space of section parameterizing a non-dominant family of section, then section parameter M will contain B. Okay, what does it mean? So non-dominant family of section, of course, sweep out some proper cross subvariety. But then a priori, there can't be many such a non-dominant family. It is a component parameterizing a non-dominant family. So if I take like an image, union of loci factorized by those non-dominant family, a priori these are a counter union of proper cross subset. But then we can actually prove that this is actually contain proper cross subset. So we can say that all section outside of B is dominant family. It belongs to dominant family. So deform to cover X. So this is a very nice theorem. And then this to prove theorem like this, we need essentially BAB. This requires BAB. To prove theorem like this, it requires BAB. And then actually this statement follows from second statement. So second statement is the following. There's a bounded family of smooth projective B varieties Y equipped with B morphism F from Y to X, satisfying that F is generically finite onto its image, but not birational. And A invariant of Y is greater than or equal to A invariant of X. And if equality of Fujita invariant is achieved, then Ithaca dimension of this adjoint divisor is 0. And then this bounded family satisfies the following universal property. Suppose we have a component space of section M that generically parameterizes non-relatively free section of sufficient large degree. Then either general section C parameter M satisfies that C is contained proper cross subset defined by this guy, or C is equal to FC prime, where C prime is a relative free section in Y, and the F from Y to X is in our bounded family. So this theorem is saying that, so basically these non-relativity sections of sufficient large anticategory all are coming from bounded family of accumulating mass. And then this requires use of like a BAB conjecture, but also this requires the use of this lemma 8.3, like a universal family of accumulating maps up to twisting. So actually, statement is very algebraic geometry, but actually proof uses a lot of number theory. Like use a lot of ideas from number theory, like a twist, and we consider like a space of twists and so on and so on. Okay, so this is the second main theorem, and this is essentially from BAB conjecture. Okay, do you have any question? Right. Right, then main theorem 3. Now, so suppose we have Fano vibration. Then there's some linear function QD whose leading constant in D is a positive number depending only on dimension with the following property. And if M is the reduced component of space of sections, parameterizing the family of sections satisfying this property, and N is the reduced sublocus of parameterized section C such that restricted tangent bundle is not generically globally generated. Then either codimension of N in M is at least grows linearly, or curves parameterized by N sweep out a subvariety Y containing X, satisfying that invariant of Y is greater than or equal to invariant of X. So what does it mean? So let's focus on case of rational curve. So suppose the B is rational curve. Then this condition is equivalent to say that it's non-free. And then so non-free loci of moduli space is essentially contains like a singular loci of moduli space. So this theorem tells us that singular loci of moduli space grows at least linearly, or there's some subvariety Y such that this is non-free curves section parameter N sweeps subvariety Y satisfying this inequality. So either codimension grows linearly, or there's some geometric reason which why linearity fails. All right, so that's the main theorem 3. And then first I should mention that this leading constant only depends on dimension, but this is the constant, effective constant depends on like some effective VAB. So effective VAB is not known, but assuming effective VAB, I believe that one can get some effective leading constant of this linear function. And then also I should mention that Tim Brownie and Sawin using a circular method obtain similar result for hypersurfaces of low degree. Okay, so that's the third statement. Right, so those are all the statements I wanted to mention. So from now on, I'm gonna explain some proofs, some ideas of proofs. But so far, do you have any question? Okay.
About your main theorem 2.
2, yes.
Can I see do you have an example about your theorem, like the X and the proper closed subset? So do you have an example?
Yeah, so let's say, how should I say? I mean, like for rational curves, it's easy. This is just like for the repeat surfaces, union of -1 curves or something like that. And then for higher genus curves, essentially this is the union of -1 curves. But there we might need to include some finitely many conics.
You say, for example, so you are saying if I consider a family Fano vibration fibered in like a Del Pezzo,
right?
And consider a -1 curve.
Right, like a -1 curves.
Family of -1 curve.
Oh yes.
Then this
or
will
like
give you,
sometimes finitely many family of conics.
And this will give you an example of the proper closed subset V there.
Exactly.
Okay.
Yeah. So yeah. I think like an example you can compute a lot, and then in the example it's not so hard to see that this is already true, but proving some general theorem is kind of, I think, is key too. Yeah. Anyway, so but that's the examples. Yeah. Any other question? All right. So then first I'm gonna explain how to prove like a main theorem 1, and then especially I'm gonna talk about this case, when evaluation map is dominant, and then moreover, I'm going to assume that evaluation map has a connected fiber so that y is equal to x. So this one is trivial. And I'd like to explain why, how to construct such a phi, rational map phi. So that's the, I'd like to something explain. So first we outline the proof of case 2 of main theorem 1. We assume that evaluation map has connected fibers so that y is equal to x. We must construct rational map phi from dominant family of non-free section. And our strategy relies on the theory of foliations and slope stability. Following version of Graham-Mills theorem allows us to compare semi-stability of sheaf E on X and the semi-stability of restriction of E to C. So Graham-Mills theorem. So suppose we have a smooth projective variety is torsion-free sheaf on X, and M is the reducible component of morphism scheme of then use the universal family over M, U nu be the normalization of U. Suppose that evaluation map is dominant with connected fibers such that for some open subset, restriction of EV to preimage of this open subset is flat. Restriction of evaluation map is basically evaluation map is flat. Then for general curve C parameter M, so we consider restriction of C and then consider hard analysis filtration. Suppose that E is C semi-stable. Then for every index I, this amount is bounded by this value. So this is basically saying that if E is semi-stable, then restriction is also almost semi-stable. At least you can say that gap between these gap between successive quotient of hard analysis filtration is bounded, uniformly bounded in terms of genus, dimension, and rank of E. So basically, it's saying that if E is semi-stable, then restriction of E is almost semi-stable. All right, how are we gonna use this? Suppose C is a general member of dominant family of non-reductive section pi with the evaluation map as a connective fiber. In this situation, a restriction of T to C is generically globally generated. So non-relative free implies that restriction of relative tangent boundary has low slope quotient. So it's not semi-stable at all. Graham-Mills theorem applied to bilateral model flattening the family yields foliation F of largest flow. That you can, so basically it says that restriction of tangent boundary is not semi-stable at all. So Graham-Mills theorem tells you that tangent boundary itself is not semi-stable at all. So you can find the maximal distributing subsieve which defines foliation. And then we appear the compound pound to see the foliation is induced by rational map phi. So here's the compound pound. Let X be a complex smooth positive variety and F be a foliation such that minimal slope is positive for some movable class alpha. Then F is induced by rational map phi with rational connected fibers. So basically, that's how you construct rational map. We construct rational map using foliation and slope stabilities. Okay? So that's the main theorem 1. Do you have any question? By the way, this Graham-Mills theorem is also some theorem we prove in our paper. We believe that this has more application other than our theorems. I mean, it's a pretty nice theorem. All right, next I'd like to talk about outline of proof of main theorem 2, boundedness. Main theorem 1 shows that family of non-free curves, non-free section come from maps such that A invariant of Y is greater than or equal to invariant of X. Lehman same to Tarima to Lehman 8.3 shows that if we base chain to the algebraic closure, then there are only finitely many family of such a Y whose twist account for rational point contribution of all maps of this type. In this way, proof of main theorem 2 is reduced to the study of twist over the ground field. So twist means that over the non-closed field, two varieties are not isomorphic over non-closed field, but after taking base change to the algebraic closure, becomes isomorphic. When we have such a situation, we say variety is twist of other. And then, so this is a, parameter like Garak homology and so on, and very nice. And then, so we systematically study the twist of fixed math. We construct space of twists and prove local to global principle. So let D and B be a positive integer. F eta from y eta to x eta is generically finite dominant morphism, where x eta and y eta normal projective variety. Let S be the set of twists of F eta sigma such that twist and y eta become isomorphic after base change of Galois extension, whose degree is bounded by D, whose discriminant branch locus consists of at most B points. Then there's a finite type of scheme R over C and a morphism UR over R and UR to F such that every twist is isomorphic to fiber of psi over some closed point. And then fiber, yeah. But anyway, so we prove that if we bound, so we have a finite space of twist. And this is like a countable union of variety, like schemes. Countable union of finite type schemes. And then but then if we say that we only look at the twist, which are split after base change by Galois extension, whose degree is bounded by D and discriminant is bounded by B, then there are some bounded family of twists, parameterizing such a twist. So this is one boundedness. So to prove they are to prove boundedness, we need to bound these D and B. D and B. So we need to say that since we are looking at split over by the Galois extension bounded degree and bounded discriminant. And then we prove the following using this, we prove the following theorem on boundedness of twist. Suppose we have a Fano vibration pi x over b, y is normal projective variety equipped with dominant morphism with connected fibers y to b, and f is dominant generically finite b morphism. Let y sigma is smooth projective b variety, and this guy is a dominant generically finite morphism such that this is the birational to twist of f eta. And t is a positive integer. There exists some constant d depends only y over x, and n depends only y over x and t we fix with the following property. Suppose that there exists some related component n sigma or space of section in y tilde sigma, parameter the dominant final section of y tilde sigma such that push forward of n sigma has a codimension atmos t in component or space of sections. Then there exists finite Galois morphism b prime over b of degree atmos d with atmos n branch points such as base change of f eta and f eta sigma to kb prime or birational equivalent. So basically twist split after I take extension Galois extension bounded degree d and discriminant atmos to n. And then they got so how to bound like this d and n, you need to bound like you need to find space of sections with this property, like has a codimension atmos to t. And then this is basically given by main theorem 1. Main theorem 1 finds like a section, such that dimension is atmos to t. Okay? So we can use our main theorem. Now, using combining main theorem 1 and the main theorem 2, this is theorem of boundedness. We can prove main theorem 2. Okay? And then how are we going to prove this boundedness of a twist? How to prove such a statement? Degree is essentially bounded by order of birational automorphism group of y eta bar over x eta bar. So this is something bounded that depends only on y and x. Discriminant is bounded by number of non-vanishing local invariants. So this involves local cohomologies and so on. The Galois cohomology, local Galois cohomology. And the number of non-vanishing local invariants is bounded by number of non-reduced fibers of Y sigma. So you can prove that if Y sigma has a reduced fiber and at that place, local invariant is 0. So basically, non-vanishing local invariant is coming from non-reduced fibers. And then number of non-reduced fibers can be obtained using canonical boundary formula combined with boundary intersection section against the ramification divider. And the boundary intersection number follow from dimension estimate and the number T. So this is how T is entered. Okay. So this is the proof of main theorem 2. Okay, so far, do you have any question?
So do you also use BAB in this?
Yes, we use BAB.
Where,
Essentially, BAB is used in this part. Like so over algebraical closed field, we find some bounded thing. And to do this, we need BAB. So so BAB is used in this part. Like to construct something over algebraic closure of function field. The bounded family of bounded family over algebraical closure of function field, we use this BAB, this part. But then we need to reduce to study of twist. And twist part doesn't use much. Actually, let me see. At some point, we actually had to use some. So I don't quite remember, but at some point, we had to use some statement about the boundedness of polarized variety in Birka's paper. So it's not just we not only use these BAB papers, but papers after BAB, we also use them. The Birka's paper after BAB, we also use his paper after BAB to prove this theorem. Yeah.
Okay, thank you.
Yes, thank you. So this is essentially required BAB. Yeah. All right, then let me explain the application of this main theorem 2. So on weak Marinus conjecture, so let F be a number field F, B is a smooth projective curve over F. S is a finite set of places of F, including all Archimedean places, and OFS is a ring of S integers in F. Let pi x over B is a fan of a vibration defined by F, and this guy, Mascal X over Mascal B, is the integral model of pi over ring of integers, such that X and B are smooth over ring of integers. And B is the closure of union loci switch parts by non-dominant family of section in space of section. By theorem 2, 1, this is a proper closed subset. And then let B is a flat closure, Mascal B is a flat closure of B. Okay? Now, let B be a non-Archimedean place of F, not containing S. And then we consider reduction at B, which is over finite field KB, and B sub B is reduction on B. And then look at this, space of section over finite field. Open set of space of section, parameterizing section, not contain C, not contain B, over anti-Cannon height less than equal to D. Then we consider the following counting function. So counting function defines the number of points on this moduli space. And then weak Marinus conjecture over function field predicts that for any epsilon, we have, so for any epsilon, this counting function is bounded by q to the d times d1 plus epsilon as d goes to infinity, where qb is the number of points on fb. So this is like a weak Marinus conjecture. This should hold for any epsilon. And then, so our theorem, assume d is sufficiently large, then this ratio goes to 0 as not d goes to infinity, but b goes to infinity. Okay, so you may think this is like a strange theorem. It's a kind of cheating, but it's meaningful because so in analytic number theory, if you have some problem of analytic number theory over function field of curves over finite field fp or fq, then first, they consider like a, so we like to we consider some analytic behavior by letting some parameter goes to infinity. But that problem is hard. But then instead of letting parameter goes to infinity, first let P goes to infinity, then parameter goes to infinity. People consider such a question. So and then we consider such a question, and we can prove such a weak Manin's conjecture in full generality in this situation. Okay, so this is like a kind of approximation of a weak Manin's conjecture. So we hope that okay, double limit exists, and I mean limit commutes and so on and so on. So I hope that this is meaningful. But anyway, so this is application. All right. So last 15 minutes, I'm gonna talk about some focus on Dirichlet fibrillation. So I will focus on Dirichlet fibrillation. So this is joint work with Brian Lehman. But so far, do you have any question? All right. So then, so this is like I mean, this theorem is proved before our main theorem, like before this paper, part 2 paper. But anyway, let X over B is Dirichlet fibrillation. That means the fiber is surface now, final surface. And then minus Kx over B is being relatively named. Then there exists positive constant C and Z such that M dominant but not relatively free components such that C satisfy this inequality. Let Q be the maximum of the number of general points contained in general C. Then Q is less than GB, and C passing through Q general points super surface such that Y eta is minus Kx over B conic. So basically, like this is like so in this case, moreover wise, yeah. So anyway, so this is like we prove this is like a instance of main theorem 1, instance of main theorem 1, 2, and then W is minus Kx conics, minus Kx conics. Yeah. So this is like a 5 out by conics. And then, so movable bend and break. So Mori invented technique called bend and break. So this is saying that if you fix two points on rational curve, and if you deform rational curve, and then it breaks into union of rational curves. And this is a very nice theorem. It has many applications. However, bend and break apparently has no control on degeneration. And with Brian Lehman, I've been proposing a notion of movable bend and break, which means that if you have a free curve or free section, and then it breaks over sufficient large degree, and then it breaks into union of free section and the vertical free rational curve. And then this is so-called like a movable bend and break. And then this is open in general in higher dimension, but we prove this for Dirichlet fibrillation with additional property, namely that assume that minus Kx is being relatively ample. Then there exists some constant explicitly computable with such that following is true. For any relatively free components, parameterizing a section satisfying this, and free section satisfying this inequality. And let M bar be the Zariski closure of M inside the moduli space of stable maps. Then M bar contains a stable map such that C consists of one section and one vertical rational curve, such that section is relatively free section, and another rational curve is bilateral mapping to free rational curve on X in the fiber. So we are saying that if you have a free section of sufficient large height, it breaks into union with one free section and one vertical free rational curve. So this is so-called like a movable bend and break. And then, so application of this movable bend and break is the following. Let X over B is Dirichlet fibrillation with minus Kx being relatively ample. Then there exists some polynomial D, such as number of components of space of section parameter section of height bounded by D is bounded by PD. So basically, we prove that the number of component of in terms of degree is bounded by polynomial. And previously known bounds for number of components of Hilbert scheme are sub-exponential. So it's much improvement in this case. So we can prove something like this using Bloomberg-Vandenberg. So this
So
is basically
the height is the anti-canonical degree of the
exactly anti-canonical degree. Yes, anti-canonical degree. So you can prove like this. And then also there's a geometric Manin's conjecture too in this setting. So suppose we have a derivative vibration, then there's some numerical class in the Nefcon curve such that any alpha in this translation is represented by exactly number of Bragg group element families of relatively free section. And the Bartel heuristic shows that this conjecture plus weak approximation implies GMC2, Manin's conjecture 2. So it says that basically you should have a unique Manin component. And then this is in the case of the derivative vibration, it's reduced to this kind of conjecture. And then we say that the derivative vibration admits global system lines if every fiber of pi is normal derivative surface with canonical singularities. And then canonical divisor L on X such that every fiber F with this is equal to 1 and this is equal to 3. So basically this is saying that this is a pullback of hyperplane class from P2. So in particular, in this case, derivative vibration is split and the genic fiber has highest Picard rank and so on and so on. Now suppose we have, no, it doesn't need to be highest Picard rank. Sorry, I misspoken. Because, but it admits bilateral contraction to P2. It admits bilateral contraction to the vibration P2. And then now, so here's the main theorem. Let X over B is a derivative vibration such that minus Kx is relatively ample, and X theta is derivative surface such that Picard rank is equal to Picard rank, geometric Picard rank, and the pi admits global system of lines. Then geometric Manin's conjecture 2 holds. That means there's unique Manin component in each class. And the proof uses monoid structure given by gluing. And so basically, this is required to use like a Bloomberg-Vandenberg plus gluing. And then this proof is interesting. So usually before this theorem, this irreducibility is proved using induction and a Bloomberg-Vandenberg. But we prove this theorem. This is the first time that we don't need to use induction degree to prove irreducibility. So usually, when you prove irreducibility of moduli spaces, first you analyze the base cases, and then use Bloomberg-Vandenberg to prove induction part. But this is the first theorem without induction. We just use Bloomberg-Vandenberg and the monoid structure given by gluing. Somehow, so yeah. Anyway. Okay, so it's a bit early, but let me finish that. All right, thank you very much.
Yeah, thank you very much for the nice talk. So are there any questions?
So in the proof of your main theorem, you mentioned something about the vanishing cycles. So the vanishing cycle related to the can you go back to the slide, please?
Yeah, sure. Vanishing cycle.
So do you mean that the vanishing cycle always contribute from the non-reduced fibers?
Oh yeah. Okay, now I understand it. Yeah, so here, yeah, so local vanishing cycle, non-vanishing local invariance. So yes, exactly. So we are looking at Garoq homology and then non-vanishing in terms of Garoq homology of local invariant, and the non-vanishing local invariant is only coming from non-reduced fibers. Yes.
And also you mentioned about the canonical bundle formula. So
right.
So what kind of canonical bundle formula are you using?
Well, we don't quite use like a very fancy canonical bundle formula. We just use that if you have non-reduced fiber, then there's some contribution to the ramification formula. That's what we that's what we use. So when you relate these y sigma and y by some, so these are two varieties become the isomorphic after taking some base change of B, and then somehow ramification formula, ramification divisor is contributed by non-reducible fibers. So if you have a non-reducible fiber, somehow there's a non-ramification divisor corresponding to this non-reducible fiber. And then that's the kind of property we use. So we don't quite use a very fancy canonical bundle formula or Mori Fujino or something like that. But anyway, yeah.
Okay, I see. Thank you.
So are there also statements or conjecture which involves B invariant in the geometric setting?
That's a good question. So B invariant is so basically, so let me explain how geometric Manin's conjecture works. So basically, like so how should I say? Yeah, so basically, like so first part is saying that each algebraic class moduli space has an expected dimension. And then for second property, statement saying that basically each algebraic class moduli space has expected is irreducible. That we means, and the third statement is saying that moduli space, number of points on moduli space is essentially Q to the dimension. Okay, and then once you assume those things and then replace number of points on moduli space by Q to the dimension, then you can count number of points by just count lattice points in the Néron stability space. Not Néron stability, the Nefcon of curves. And then you count like those Q to the B, and then like you have how many classes do you get? Basically, you are counting like a number of classes in the cone, right? Nefcon. And then that gives you like a D to the Picard rank -1. Do you understand what I mean? So basically,
Sorry.
like
Yeah, maybe I missed something elementary. So if the dimension of this main irreducible component is positive, then how do we count the point in?
Yeah, so that's so idea is to use Grothendieck-Lefschetz trace formula. So idea is to use Grothendieck-Lefschetz trace formula, and then you combine with homological stability. We are hoping that we can prove that number of points on moduli space is a Q to the dimension. But this is not, and okay, this is the reason why we say this is heuristic. So we don't really have a actual concrete proof of this part. But anyway, suppose that number of points on each component is given by Q to the dimension, and then naively count the points on that. So weighted counting over lattice points of Nefcon. That gives you like a simple formula of Manin's conjecture. Q to the D times D to the Picard rank -1.
Okay.
So yeah, so
Like
that's
up
the
to-
heuristic how it works. Yeah.
I see. So it's like up to some homological equivalence.
Yeah,
or-
exactly, up to homological stability, which really we really don't know how to formulate more precise conjecture, to be honest, this part.
Yeah, maybe this is related to my second question. So is there precise statement of or how precise statement do we have about geometric Manin's conjecture?
So first one and the second one, we have precise statement. And the third one, we don't have a precise statement.
Okay.
But this is only in Category 0. Category P is another problem. Like it's another issue. Like, there are real component and non-separable components and so on. So I mean, there are many kind of strange things happen in Category P. So we know how to basically formulate geometric Manin conical 1 and 2 in Category 0, but I don't know how to formulate in Category P, Category 0, third part. And then in Category P, even first statement, we don't really know.
So are there more questions? If there's no more question, then let's thanks Professor Sho Tanimoto again. Thank you very much.
Thank you very much.
Yeah, so yeah, maybe it's already dinner time for you. Right?
Yeah, yeah.
Mhm.
All right. So
Yeah.
I have to go home. Yeah. So
Okay.
I think I will say goodbye here. Yeah. Thank you for
Okay, and
inviting me.
yeah, thanks
And,
for giving the talk. Yes. Yeah, I
Yeah.
hope that see you soon somewhere someplace. Yes.
Right.
Okay, so take care. Bye bye.
Bye.